Good morning, everyone, and welcome to Automating Your Lab using Green Button Go. My name is Jerry Alden. I'm the European Sales Manager for Biosero, and I'll be moderating today's event. We have a great agenda planned for you today. First, we're going to hear from one of our most experienced automation specialists about optimizing Workcells using Green Button Go, followed by our European Customer Success Manager about ways to fully integrate your lab operation, including the use of mobile robots. That said, we're most excited about Dave McClymont from Horizon Discovery sharing his insight into automation at their lab. So before I introduce Tim, a couple of housekeeping items. If you've not already done so, please participate in the poll questions that we've put forth. It's the third tab in on the right-hand section of your screen. With all of us working from home, you've probably attended several of these webinars recently, so you know that you can put questions in the chat box or question box at any time, and we'll discuss these at the end of the three presentations respectively. So yeah, feel free to use the chat, share ideas, and interact throughout. So with that, let's get the thing rolling here. So I'd like to introduce Tim Karsten, Senior Automation Specialist to Biosero. Prior to joining us here, Tim worked as an application specialist for a major automated liquid handler company, and also as an in-house automation expert for two of the most prominent therapeutic startups in the Boston area. During this time, he implemented and supervised automation projects, including NGS sample prep, automated cell culture, and enzymatic assays. Beyond this, he also has a strong background in software deployment and LIMS integration. Tim received his Ph.D. from the Veterinary University of Hanover in 2013, and it was titled Interspecies Transmission of Zoonotic Coronaviruses. Over to you, Tim.
Hi, my name is Tim Karsten. I'm the European Application Support for Biosero. Today, I'm going to talk about the challenge for many laboratory managers of how to sustain their laboratory output during the current COVID-19 pandemic. The general benefits of automation in labs are easily apparent. An increased throughput by freeing up humans from repetitive work, which also results in better scalability and long-term cost savings. The quality of data your lab generates is improved by removing human error, offering complete audit trails for process improvements. Safety of operators and samples are of course a special concern handling clinical samples or live pathogens. And research companies prove repeatedly that the investment in lab automation is returned by an acceleration in discovery. The core tenets of an automation software that drives an integrated work cell are 5. It must be easy to use and approachable, while being powerful enough under the hood to implement the most complex workflows. It should be agnostic to hardware. By decoupling hardware from software, the customer is able to select the devices which are right for the job. It needs to be flexible to accommodate changes in workflow or hardware composition easily without downtime. And of course, it should offer scalability from one validated system to X number around the world. These are the guiding principles for Green Button Go, our software offering to the market. Green Button Go, or GBG, is 100% hardware agnostic. Any preference of a particular brand or device can be accommodated. Maybe you start with a particular brand of liquid handler, but later want to switch it out? No problem. You already have a certain incubator or plate hotel you want to reuse? We support that. As long as it's somehow plugged into a PC or network, we can automate it. All our drivers are written as software plugins. That makes them easier to develop, maintain, and update them when the need arises. Green Button Go is a proven, battle-tested software. We have already automated a wide range of processes and applications. We deliver simple systems where, for example, a stack of plates needs to be fed to a reader, a liquid handler, or any other standalone device. Interestingly, several manufacturers of complex standalone devices have already chosen to rely on Green Button Go when they want to offer more throughput-centric solutions of their own. Also, devices which have not been originally designed to be accessed by robotic manipulators can be automated by custom grippers or handlers, like for example the LCMS system in the upper center of this slide. Screening pipelines are a common workflow we automate for customers, as they have a well-defined process steps with minimal variability, but have highest standards for sample and data integrity. As you can already tell, we can offer any kind of configuration and even work with providers of professional safety enclosures to realize partially or completely enclosed systems as well. With the advent of collaborative robots in the labs, the boundaries between human and robotic operated workflows start to disappear more and more. This rings even more true with our introduction of mobile platforms. Rob Harkness will talk about that in more detail. To be successful in any kind of lab, automation needs to be easy. Training somebody to operate a system must be straightforward without any ambiguity or stage fright. For that reason, GBG has a built-in basic screen, which is automatically generated for each workcell process you design. Have somebody walk up to the system, select the process they want to run, enter the number of plates, and go. This is the power of Green Button Go. On top of that, we can implement full FDA Part 21 CFR 11 compliant user access control, a unique feature to our application on the market. But under the hood, GBG is immensely powerful. During runtime, you have real-time information of device status and plate positions, even on integrated liquid handlers. If a process needs tweaking, you can climb down the ladder of abstraction to the level of single hardware commands. You can write custom scripts in 4 different high-level languages, or interface with any kind of limbs you love or have to use. GBG offers scalability on many levels. Our device utilization dashboard helps you identify execution bottlenecks. Plates are waiting to get sealed. Just add another sealer to the device pool and you have automatic load balancing. You have multiple identical work cells? No problem. Copy the processes, maybe change the IP addresses, and you are good to go. But GBG is also flexible. You can easily add custom user screens like shown here, or even interface with your work cell through mobile devices. GBG sits at the center of our product suite. It integrates into any data service needed, can communicate with your inventory management, or talk to any form of business intelligence or data analysis software. Our product suite has you covered. If you're at the start and your workflow is purely manual, our lab experience software can guide the user through the process steps. When you then add simple devices, our IoT solutions can integrate your water bath, room light, freezers, etc. If you then wish to step up to an integrated work cell running GBG, your operators are already trained on our products and are ready to go. And when the need arises to connect many work cells, we can orchestrate that too using GBG Order Manager. I would like now to switch to GBG and give you a demonstration on how simple it is to implement a common application. Here we are now in GBG, and this is the basic run screen I shown previously. Let's switch to the full editor. You see, GBG is logically structured into 6 panes, and we go from left to right. To quickly go through a new work cell process, let's start with the layout. In the layout, you will drag and drop the devices you have on your work cell and resemble more or less what you have as a physical representation to help you later on troubleshoot and supervise the system during runtime. Here it is not necessary to match the position of your devices specifically, because this is just a visual cue on what is doing right in that second. Devices currently executing during runtime will be highlighted in greens, those in error state in red. When you pull in a new device, the device process steps become available in the Workcell process. In this Workcell process, we will have one play process, as this is a very simple Workcell and a very simple application for our demonstration. So this play process will pull a plate from the hotel from a specific zone, and at the end, it will return it to the same zone. In between, we will have a dispense, and then we will seal the plates. You have noticed that there are no robot movement steps involved. This is all handled by GBG in the background. So this now is a very simple application workflow, but now see how this is getting executed. When hitting the run button, we are jumped forward to the run screen, and the first thing we will see is the inventory data. Here we tell the inventory that 3 plates are loaded, and the Workcell process will continue to execute. On the left side, you will now see the respective device lighting up in green when it's currently executing a process step. We have the ability to pause or stop the execution up here. And in simulation mode, we have also the ability to speed up and slow down the simulation time. The Gantt chart over here is now showing for each individual plate in this plate process the steps and how long they took. So far, this might be very familiar with other automation software, but yes, this is especially the layout window is a nice indicator for an operator of what is currently happening, and if a device is in an error state, of how to identify that. And from the layout screen, you have the full ability to modify all of the devices and even put some in simulation mode or execute single steps. So you've seen we created like a simple application workflow in GBG in a few minutes. Now let's jump out and go to a predefined layout I created previously. This will more or less resemble what we would consult for as a ELISA platform. It has a plate storage, a robot arm, a plate washer, incubators, bulk dispenser, a plate reader, a centrifuge, and in this case also a complex liquid handler because I included a 4:1 reformatting. When we look at the Workcell process, I called it COVID ELISA, and this Workcell process has 3 different plate processes: sample plate, ELISA plate, and tips. The tips will be used up on the Bravo and then disposed. The sample plates will also only move to the Bravo. Then a small sample transfer will happen, and then they move back to their original location. The ELISA plates are the heart of this application, and they will be initially empty, and then they will receive a bulk dispense. They will move onto the Bravo, will receive a small subvolume of sample, and then they will move onto an incubation step. The incubation will happen in an instrument pool. So GBG offers the simple solution of how to handle multiple identical devices and the load balancing. So this device pool is now selecting one of the included devices based on availability, but you can also spread out the load between devices evenly if you desire. After that, there will be a plate wash, a bulk dispense, a read, and then at the end, the ELISA plate will be disposed. So when you run this, which I've done here previously, and you look specifically at the ELISA plates, you will notice that the incubation time is the longest step in the overall workflow. And as we only have 2 incubators available, the third plate starts to be executed fairly differently from the other ones. The first plate rushes through the multi-drop dispense, then goes to the Bravo and goes onto the incubator. The second one is actually waiting on the multi-drop after it got the diluent dispense on the availability of the Bravo, and then will move finally to the incubator. Third plate will also wait on the multi-drop, but then later on it will wait on the Bravo for a prolonged time for over 20 minutes on the on one of the incubators becoming available. So usually with sample plates, this is not what you desire because you want to process them more or less in the same way to prevent any process differences. And we're now going to talk about how you can steer the process execution in GBG to make that happen. GBG has a dynamic scheduler, so it's not a sequential execution, but it's every process step is evaluated for its ability to being executed constantly in cycles, and you can prioritize certain plate process entirely over different plate processes. But you can also prioritize individual process steps over the rest. So in addition, at the moment, all of these steps are prioritized identically. So that would mean when the scheduler sees these at the first time, it will more or less choose randomly, and then it will decrease or increase the priority by a certain aging factor, and then walk through the next cycle of evaluation. Currently, we don't have a problem with the competition of the plate processes over device resources. The problem is that these processes are taking too long, and that this plate here is sitting idle outside with already diluted sample on top. So one solution for that would be to employ what we call a ready evaluation. So the ready evaluation will be influenced now by the availability of the next step. So we won't execute the Bravo step until one of these two devices becomes or is available. We will also do this with the multi-drop combi, so that the ELISA plate will actually not come out of the incubator until both the Bravo steps and the incubator instrument pool become available. So let's see how that looks like. So we are greeted with the inventory window again. Right, okay, confirm the loading. Now we will concentrate on the ELISA plates. You can see during runtime that GBG is indicating the position of each individual plate throughout the whole process. So at any point, you can pause the process and look at the devices and see where currently plates are located. So currently we see on the Bravo, there are 4 plates loaded and 4 sample plates. So probably next will be the retrieval of the tips, and then we will see the ELISA plate move out to the bulk dispenser. There are our tips. And now we see the first ELISA plate coming out. So the ready evaluation is now limiting the second ELISA plate from coming out and moving onto the multi-drop because the Bravo is still occupied. This is already one difference to the previously shown run. Now that the Bravo has become available, the multi-drop becomes available, and we will see the second ELISA plate moving out eventually after the Bravo has been unloaded and loaded. So this is one way to steer the process. You can obviously, even during runtime, add additional devices to the instrument pool. So let's say maybe you have a long run and one of the devices became unavailable. Then even during the run, you are able to add third incubator to the layout. And you would also be able to add this third incubator now to the instrument pool during runtime. So that is a different way to prevent your deadlock or your method execution from being slow. You can now see that the third plate is not coming out and that those two plates are processed more or less identical. There is a second way to get to the same result. Stop here. Stop the process. We can also take back this ready evaluation, and we have the ability to limit the number of plates which are simultaneously executed to a certain number. So in this case, it would make sense to limit the plates to only being 2 ELISA plates executed simultaneously. This will eventually lead to the same result. I'm running short of time, so I'm not running through that. The third and probably most used option is to limit the release of new ELISA plates from plate storage. We have seen previously that the incubation on the incubator is taking about 30 minutes. So if we only release a new plate every 15 minutes, that would also lead to the result that the plates are more or less handled identically, as there is no competition over devices in the overall workflow. So I hope you got a good impression of that GBG offers many possibilities to control the workflow execution, the Workcell process execution. Of course, I have not the time to go into all the details. We can also gate the execution by setting triggers or even skip certain steps by evaluating certain variables or executing scripts during runtime. Yes, this will be the end of this GBG demonstration.
Thanks, Tim. Let's go to some questions now. So, Tim, how does a device pool react when one of the devices is in an error state?
Yeah, this is really one of our strengths. We can modify the device pool during runtime. So you can put certain devices in simulation mode, so taking them passive offline. During runtime, if they become unavailable in an error state, there is even the option to include hot spares and react on certain availabilities and even include devices to the layout at runtime. So that is one of the strengths of GBG.
Excellent, thank you. Have another question here. Can you start Workcell processes based on the results of a previous process, a previous run?
Yes, so you are able in GBG to pre-schedule Workcell processes into the future or make them dependent on the end or on the execution of previous Workcell processes. So you could even employ, let's say for a cell line development project, you could create and schedule new Workcell processes from a currently executed Workcell process ahead of time. Thereby making the whole Workcell even more walk away and more dynamic to the state of execution.
Excellent. Thank you. Thanks, Tim. Right, shall we move on to the next talk? Happy to introduce someone that many of you may already know. Rob Harkness has worked for over 20 years now delivering laboratory automation solutions to both the life science and consumer products business sectors. Rob received his degree in computer-aided chemistry from the University of Surrey in 1999 and a Ph.D. for his work titled Novel Software Solutions for Automating Biochemical Assays in 2010. Rob's enjoyed a variety of roles throughout his career. He initially started as a programmer at PAA, developing a scheduling software package for controlling robotic arms within an automated platform, and has since enjoyed several roles at PAA, Analytic Jena, SciBio, and Aztec projects within software development, project management, and business development. And he's now working with us here at Biosero as our Director of Customer Success for the UK and European territories. Rob also serves as a director in the Standards in Laboratory Automation Consortium, more commonly known as SELA. This is an effort from within the life science community to create open system communications and data standards. So with that, over to you, Rob.
Hello everyone, my name is Rob Harkness and I'm the Director of Customer Success for Biosero here in Europe. And in this webinar, I'm going to show you why we need flexible software for dynamic assays to support digitalization initiatives and how at Biosero we have the tools available to support end-to-end integration. Now, to start, I want to cover what integration is. And in simple terms, it's about allowing various independent components to work together with some form of benefit. Historically, integration or connectivity has significantly impacted our lives. Before the first industrial revolution, business was very regional as transporting goods was difficult. The increased use of rail suddenly allowed producers of goods to distribute their product on a much larger scale. A great example of this was in South Wales, where the Taff Valley Railway connected the Welsh coalfields with the seaport in Cardiff. It was only 30 miles long, but when built, it meant their coal could reach a much larger market. It became the coal centre of the world, increasing its output by over 3,000% over a 30-year period. And this happened because of connectivity. Integration and connectivity benefits all of us. Think of where we would be without the internet, which you're using right now. But integration can be complicated, especially systems integration. Technically, it normally requires teams of experts. And then there's the change management aspect, where even the best initiatives can be derailed by perceived issues. Things are changing though, and tools have appeared with a real focus on making integration simple. Take the home automation market. I'm sure many of you have at least one of these devices in your home, be that an Amazon Alexa, a Google smart speaker, lights, TV, and so on. These devices are great on their own, but the value of my Google speaker increases exponentially when I have the power to link to other devices or services. I use If This Then That, a web app with a real simple interface for this, and have applets set up to alert me when my outdoor Nest camera spots someone outside approaching the house. And I have another one to turn off the lights in my children's bedrooms when I say, "Okay, Google, turn kids' lights off," as they always leave them on. Now, this type of software is called RPA, which stands for Robotic Process Automation. It's not a robot in the physical sense. Think of it more as a software agent that performs a set of actions based upon predefined rules triggered by some event. These are very useful when you automate the repetitive tasks that you do day in, day out that are prone to error. Now, the example I'm showing you here on screen shows the savings that can be achieved by using RPA to process and analyze inbound emails. Now, this process was taking 2 hours, but now takes 8 minutes. Combined with the fact that this process rarely makes mistakes, you have significant improvements, all made possible by integration. Now, digital transformations are happening everywhere and across all industries. Take RPA, heavily used in the banking sector, where we get the right result, decision, or calculation every time. Complete audit trails, essential for compliance. We free up people for more value-added tasks, and we have the ability to instantly ramp up or down to deal with spikes in demand. These are all benefits that labs want too. Digitalization can really help with the reproducibility crisis that exists, addressing root issues such as scientists having to repeatedly input the same barcode manually into multiple systems as part of a single workflow. Now, one type of digital transformation that we're seeing become more common is end-to-end integration. The goal of taking a lab workflow and managing it from start to finish. Now, whilst desirable, it doesn't necessarily mean each step is fully automated in a physical sense. People can still be involved, but the goal is that the data flows seamlessly from beginning to end. Now, take a workflow in a pathology lab. Once a set of tests have been ordered against a sample, the process from accession through to result should be seamless. People may still be moving samples between steps in the process, but they're told what to do in a controlled manner. Now, I heard a recent talk about digital transformation that's about people, not systems. And this is true. It's important. Everyone involved in the lab understands this vision, that everyone contributes to ensure that these initiatives really do make a difference and that the people with the right skill sets are involved from the get-go. However, you must also have the tools available to do this. We must be able to take the different instruments we find in labs, LIMS, electronic notebooks, sample management platforms, and integrate these to allow orchestration of experimental workflow tasks. Now, the flow of data is crucial here, and we must be able to integrate this easily and securely. Connections to data analysis tools that themselves can employ AI open up so many possibilities. And only then can we really say that we have a solution that enables decision makers to make better decisions in less time using more data. Now, with this vision in mind, when we are looking for a laboratory automation tool, there are points to consider. It should be dynamic and flexible. Executing rigid workflows is great for some assays. However, what if we have an assay whereby the incubation time needs to be increased based upon information acquired during the run? A flexible system can do that. Whilst a good scheduler will plan for plates to be incubated to the required tolerance, a smart system will decide to not process any plates that are out of tolerance. Connectivity with data and instruments is a given, but we need to be able to configure this easily and fast. It's imperative that the tool can acquire data, work with tissue and mosaic, for example, or elemental machines, remote monitoring platform, and consume this data too, be able to contextualize it for other activities downstream. Now, all of this is great, but if the tool is not reliable, it's all in vain. Being resilient is about being able to handle the inevitable errors that occur when you're connected to such a variety of lab components. The database connection that drops off every day around 10 AM for no apparent reason, causing a timeout. The clogged lines on the dispenser because the buffer you're using has precipitated. A resilient tool can handle these kind of things. Okay, so what I'm going to do now is go into Green Button Go, or GBG as we call it for short, and set up a dynamic assay. For this example, we'll first run process 1, as you can see on screen. That adds compounds to a test plate, incubates, and then performs an absorbance read. And we'll then run process 2, which is imaging the same test plate, but only if the results from the absorbance measurement within process 1 meet a certain threshold. We will not know which plates will be imaged in process 2 until we start acquiring results from process 1, hence the dynamic nature of the assay. So this is Green Button Go. I'm currently on the layout screen here, and I've already configured all the instruments that I want to use. I'm not going to go into too much detail about this right now, but just wanted to point out with the incubator that in here I have defined some zones. So zones allow me to store plates in a particular area within the incubator, which just makes it a little bit easier sometimes for the operators of the system to know where their plates are. And in this case, I've got zone 1, I've got zone 2, and I've got zone 3. So this is the layout. This is already been set up. Let's go and have a look at the process now. So I've got a Workcell process 1. I have a test plate going through the system, which will have reagents and compounds dispensed to it. It will then incubate, go onto the plate reader, and go back to the incubator. So I've got compounds coming onto that test plate. So we have a compound as well going to the liquid handler. We know where to put plates on the liquid handler through using sequences. So this allows me to say that compound plate goes to position 1, test plate goes to position 2, and then I can run the native software that comes from the liquid handler. So in this case with Hamilton, I'm using the Venus software. Okay, so this is quite a fixed process. plates just go to the ferrostar and then go back to the incubator. If you remember, what we're trying to do though is take the results from the plate read and decide then which plates will go onto a second process. So I have one here called Workcell Process 2, which will take plates back out of the incubator and then put them onto the image express to image. So to make the decision which plates do actually go into Workcell Process 2, what I need to do is add in a procedure after the ferrostar has generated results. And I've already written a procedure called evaluate first image. So let's go and take a look at that. So this is where the advanced screens in green button go. And this is where I can build up procedures. And what I have here is something which, when it runs, it will run this script, which will get the detect level. This is a GBG variable. And if that number is above 50, the plate will go to zone 2. And it's any plate that goes to zone 2 will then go onto that next process, which goes onto the image express reader. If the detection level is below 50, it will just simply go back into the incubator and remain there. That's it, it's done. So if we look at the script, I've just created a very kind of a mock-up here showing how I could call a web service somewhere to take the results from the ferrostar and then just spit out a number, which is between 1 and 100, which goes into this GBG variable called detect level. Now, this is the bit where it gets interesting, which allows us to integrate with other systems. There's no reason why we can't call a web service to any other piece of software that you may have. So from Dotmatics or Benchling or Gene Data Screener or 9, we can pipe data to those services and allow them to process that, process the results to actually then decide how GBG should next proceed with processing the workflow. So, as I say, once a plate comes through here, we'll evaluate that and then decide where plates go back into the incubator before they're then run through Workcell Process 2. This same functionality can be used to set up closed-loop experimentation systems. So you can take the results, send the data to another service to analyze, come up with new optimized experiment parameters, and suddenly you've then got the ability to run a design, make, test, repeat process that is quite desirable in some cases. Okay, so I've briefly shown how GBG is dynamic and how it connects to instruments and data. I'm next going to show you how it deals with errors. All of our 300 plus instrument drivers are developed with resilience in mind. However, we can't preempt all of the issues that arise, but I'll show you now how we can handle these. So let's create a new Workcell process, which is going to put plates onto a multi-drop. So this is Workcell process 3. Let's get a plate from a hotel. We're going to do a dispense on the multi-drop, protocol test, and then put that plate back into the hotel. And before I run this, I'm just going to go and modify the multi-drop combi dispense start. So in here, I'm going to go into simulation and get it to simulate an error, which is called webinar error. Okay, so let's run the system. Workcell process 3. So we're going to run 3 plates through the system, and off we go. And what we should see, there we go. So as soon as the plate went onto the multi-drop, we've generated an error, webinar error. And we can retry. Of course, that's going to come back with an error again. So one thing we can do is then in the error manager, decide how we want to respond to these errors going forward. So the default is always to alert the user. But what we could do is just ignore it. And if I close that now, hit retry, the run will proceed. So that plate will be put back, and then we'll get the next plate out. So let's pause the run. Let's go back to the error manager, and let's turn that back to alert user upon error. Okay, so we've now got the error again. What I can do is also modify procedures while the system is running. So if I go into advanced here, I can turn the simulation off. Then if I hit go, the run will continue. That's a really nice capability, certainly when you're first building a system, where you can actually address any errors in the procedures that you've written during the run. Also, on that error manager, you may notice you can also report that error directly to Biosero. So it collates all the information about the error and will send it directly to us, generating a support ticket, which is another really cool feature. So finally, what I wanted to show you is how we can address any incubations which run over spec. So if we go back to the process, Workcell process number 1, you'll see here on the incubation that we have some properties with that. So we've got 60-minute incubation, and we say the acceptable deviation is 5 minutes. And what we can say then is if any incubation takes more than, in this case, 65 minutes, the system will automatically cancel those plays. So in this case, it wouldn't go onto the first star for reading and evaluation. So therefore, would never go onto Workcell process 2 either. And you can adjust these values here depending on how tight you need those tolerances to be. Unfortunately, most of the time the scheduler will schedule to that time. But if there was an error, like we just had there with the multi-job, then it can have the effect of stopping GBG from unloading plates during that time. So there may be like 3 or 4 plates out of your batch of 50 where the incubation is taking too long. So the system will automatically cancel those and then tell you at the end of the run which ones weren't run as well. Before we finish with the software control, I just quickly want to show you some work we have going on where instead of GBG being in control and in charge, it is controlled by another piece of software, which in this case is the KNIME Analytics platform, open source software for data science. Now from a KNIME workflow, we have a node that will get GBG to perform a plate read and then return data for a dose response calculation, all done within KNIME and communicating with CEDA2. And this is an ongoing collaboration between Biosero, KNIME, Cerebra, and Hit Discovery Constants. And we plan to share more about this at the SLAS 2021 exhibition. I'm now going to briefly discuss how mobile robots can enable the physical element of end-to-end integration. Now, traditionally, we arrange instruments around a fixed robotic arm. Using mobile robots is a complete paradigm shift, whereby the automation moves to the instruments instead, and they're designed to work collaboratively alongside people in the lab. The other clear benefit is the infrastructure change required is almost non-existent. Now, I'm sure many of you have seen videos of mobile robots whizzing around warehouses, depositing goods to different locations. The laboratory environment is very different, but mobile robots are being used here. Now, I'm showing you on screen the mobile robot that Biosero has installed at a number of sites. But there are others, such as the mobile robot POC delivered by Assay projects, Unite Labs and Roche, the KUKA mobile robot University of Liverpool, and the Fraunhofer Kevin robot. All of these are similar in that they have 3 key components. We have the automated mobile robot, AMR, a collaborative robotic arm, and a method to determine the position in space of the mobile robot in reference to the pick and place location. Now, this is needed since the AMR has a positional repeatability of around 10 centimeters. Once the camera can identify and determine the 6T pose of the glyph marker that we use, we can then convert that into a form that the robot understands to pick and place labware. And this mechanism means that you never have to reteach the arm again, provided that glyph remains fixed relative to the pick place location. Now, we're using this same technology with our mobile Workcells at Biosero too, and we've found it to be really robust. Now, there are a number of ways we can use mobile robots in the lab. We can transport plates between Workcells. These can be GBG-powered Workcells, but there's no reason why we can't use other software solutions too. We can also use just the AMR to transport microplates, so there's no robotic arm mounted. The robots on each Workcell in that case would then load and unload plates onto the AMR. The 2 Workcells can be in different labs as well and on different floors within the same building. With the right infrastructure in place, the mobile robot can actually use the existing elevators as well. We can also transport plates between instruments, replacing the need for a fixed arm. Instruments can stay where they are in the lab. They can even be on other sides of the room. There is great flexibility with this, as new instruments can be added really easily, far easier than if you were using a dedicated work cell. And the mobile robot can also be shared amongst different groups of instruments running different workflows too. Mobile robots are cool. They certainly attract interest. However, they are a serious proposition, ready for real use, not just proof of concepts, and certainly worth considering for your next automation endeavor. So that's about it. Before I finish, I want you to think back to the home automation example that I gave earlier. These out-of-the-box solutions are great on their own, but when you integrate and connect them up, their value grows exponentially. The lab is no different. Automation is already happening. A stacker feeding a plate washer right up to a large multi-arm screening platform. However, if moving data from upstream or downstream, interacting with your LIMS or ELN or analysing results still requires a great deal of effort, your lab is not running as efficiently as it could. And you should expect more, especially as the tools exist for end-to-end integration. Now, there are several providers in this space that can deliver end-to-end solutions, but I'm meant to show you that with Green Button Go, it's something you can do yourself. It's not a black box. You have full control. And if you are interested in learning more about this, or you have an idea to share, please do not hesitate to get in touch. I'd love to learn how your lab is working and see what we could do together to get the best out of it. Thank you for your time.
Thank you, Rob. I was just struggling with my my mute button there. The curse of video calls. So I have a few questions for you, Rob. How easy is it actually to deploy a mobile robot in a lab?
It's certainly easier than installing a traditional work cell. I mean, normally you get it delivered on a pallet, and you can drive it off that pallet then into the lab. So you can be up and running certainly well within a day. The first activity is to drive it around the lab so it knows the environment it's working in, and then you can define positions for it to go to. Different vendors have different ways of setting up that mobile robot, and as I touched on in the talk there, it's all about being able to detect these QR tags or APL tags, the position by the devices. But we set a lot of that up in the factory first of all. So in theory, it's less than a day. I think, as some of you may know, though, you're on the call from experience, little things do come up which cause issues, but it's certainly set up to be deployed a lot faster than a traditional automated system. And I think that's one of the reasons what makes it quite attractive, because you can set it up in one lab for a couple of weeks and then move it over to another part of the building to do some other work quite quickly. And that's a real advantage of this approach.
Thanks, Rob. You talked about automating and controlling manual processes within the lab. How would you actually do that, since your demo focused on an automated system with a robot arm?
Yeah, I mean, from GBG's perspective, it doesn't matter if we're using it, it doesn't matter if we're scheduling a robot or a human, actually. So we can direct users to do particular tasks. So we can have a screen come up on, we can have custom dialogues in GBG which come up and guide that user through the process that you're trying to automate. We also have another product called Lab Experience, which is really geared towards guiding users through those manual steps. So that could be, how to use a pipette, which wells you need to dispense to on that plate. It could be, just taking a sample over to a balance. And then behind the scenes, we're doing everything automatically. So you're not having to type things into LIMS anymore. We're making that connection automatically. And the glue behind this is something which we call data services. If anyone's interested in finding out a bit more about that, then please get in touch.
Thanks, Rob. A couple of questions have come in whilst you were talking from Shivani and Tom. Guys, I do have specific answers for you. I think in the interest of moving on and getting wrapped up in the 10 minutes we have left, hopefully you don't mind if we defer and move on to the next presenter. We'll definitely be in touch with you and answer your questions. So Rob, thanks again. Let's
Okay.
move on to our last speech, excuse me. So we saved the best for last. So it's my pleasure to introduce Dave McClymont from Horizon Discovery, where he's the head of automation. So Dave leads the platform innovation product team, which brings together cross-functional skills in automation, assay development, design of experiments, bioinformatics, LIMS, and software development. Previously, Dave designed and built the metabolic pathway engineering system known as AMOS, for yeast and E. coli at the London DNA Foundry, which is co-located within Imperial College in London. He was also the head engineer at the chemical biology platform in Oslo, which is the National Centre for Chemical Biology, with a focus on immunology and personalised medicine. Dave also worked within automated electrophysiology at Zentian Discovery, which is also in Cambridge in the UK. Dave holds a Ph.D. in molecular pharmacology from the University of Nottingham. And with that, over to you, Dave.
Hi, my name's David McClymont. I'm the head of automation at Horizon Discovery, and I'm here today to give you a presentation called Building the Foundations to Scale. So before Horizon, I was the head of automation at the London DNA Foundry, where we built the software and the robotics infrastructure for high throughput metabolic pathway engineering. Before that, I worked at NCMM, which was the National Centre for Molecular Medicine in Norway, where we did large numbers of high throughput screens for cancer and neuroscience, as well as building a platform for personalised medicine. I started my career at Zentian, where we did automated electrophysiology in collaboration with a pharmaceutical company who was developing pain drugs. So the theme that runs through all of these positions are that really science is just about moving tiny little bits of liquid from one place to another. But how do you take those movements and turn them into advanced screening and manufacturing platforms? Liquid handling robotics have been around for years and people have done great things with them. Analysis, database, LIMS and schedulers are all things you can buy. But why do I still believe there's a massive opportunity to unlock that scale? Because once you have all that technology, you're still left with a final problem. What liquids need to move around and when? And I've been trying to bring together a range of skills to that problem space in my team called Platform Innovation to approach that problem so we can unlock that scale. So Horizon Discovery is a company where the cell is at the heart of everything we do. And we've got unrivaled experience in cell line engineering for over a decade, from AAV all the way through to CRISPR. And that cell line engineering technology can feed all sorts of other areas of the business, particularly functional genomic screens. We have other business units, particularly RNA and DNA synthesis, CHO bioproduction, as well as diagnostics. So why do I feel there's still opportunities to scale? And I started to think about this when I was asked to write a paper for NATURE Biotechnology on the Maholo robot on the left. So there they had a humanoid robot that would pick up pipettes in the same way any scientist in the lab would, move liquids in and out of tubes and tubes in and out of instrumentation. But to me, that showed a fundamental misunderstanding of how you scale things in the lab, because the rules you learn moving things around by hand don't necessarily translate to the automation and microtiter plates. So it really showed me that there was a large misunderstanding for people who weren't familiar with the field. So what would I consider, a core set of functionalities you would need for most scientific operations? You need to move tiny liquids around, as I've said. You've got tip-based liquid handlers, acoustic dispensing, multi-drop, as well as putting those liquids in microplates. You might want to spin them down. You might want to open and close the containers as necessary. So with good assay development skills and instrumentation that you can buy for each of those areas, these problems have been solved. But how do we bring these together with a good software platform and a good technology platform so we can focus our efforts in thinking about what liquids need to move and when? So with my team Platform Innovation, I've been trying to bring lab-based scientists together with other types of technology specialists, custom analysis people, software development, bioinformaticians, liquid handling and Workcell automation, as well as LIMS and scientific database developers. So by bringing these people together with the right technology, I think that's how we open up our opportunities that are currently untapped. So while for many years you could go out and buy Workcells with different instrumentation in it, My experience is that the limitation has quite often been in the software. And by, when you get a system in, that's when the real hard yards happen with regards to learning how to use the software and program it for different functionalities. So I was looking for a type of software that would give me the ultimate flexibility. User interaction was keen for me. How do we program it? Graphical programming. Can we get into advanced function with scripting? But for me, having the ability to create bespoke graphical user interfaces for the end users was important for how our workflows work at Horizon. I think openness is a key. Rather than locking things down unnecessarily, be supportive of, a rapid prototyping ethos. Let me build a homebrew driver if I want. Let me make custom cloud integrations if I want. By allowing me the ability to rapidly prototype and come up with new ideas, that gives me the flexibility to respond to changing needs in future. But however, robustness is also important. Stress-tested drivers that are used in the field are always worth buying, and also having a large library of drivers allows me to change the configurations quickly. And having software as a core product gives me confidence that the software will be continually updated to changing needs. So I think, any product that you buy has to be tested in-house without people overlooking your shoulder. So we, like a number of companies, we have various, automation platforms and equipment around the building. So we wanted to get Green Button Go in, test it out, and do a proof of concept on our current systems. So, we came up with some standard assay scenarios, move plates into the echo, add liquids on the multi-drop, standard things that you would expect to be able to do. But then we added other things like, we had a homebrew driver. Could we build out a homebrew barcode reader? Could we build a driver for it? Could we do scripting and hook into the cloud? Could we develop the end user interfaces that abstract away the problem space so that the scientists can only focus on what they need to do day to day? And we found that when we had Green Button Go in our own hands, that we could meet all those requirements, so we decided to go ahead. And what we wanted to do was to integrate a microscopy instrument, which obviously has a lead time. So traditionally that lead time, you would be sitting around waiting, essentially doing nothing until it appears. But because Green Button Go has a full simulation environment, we could use that to phase 2. We could become more experts. We could train other people in the team. We could also then start to build the integrations into all our different data systems, so that by the time the instrumentation arrived, we were experts in the system. It was already set up to be hooked into all the databases and pipelines, that by the end of the day, we had a fully operational and production system. So with a software platform in place, I could start to then wind back and think about the Workcell. What if a Workcell were like a standard platform, like a PC, where you had functionality on there that you could expect on different units, rather than design around applications? So designing a system for applications makes sense, but there is always trade-offs, particularly in the instrumentations that you can put in there. So I started to think about base functionality. What are the things that you would use in any assay? You would have liquid handling. You might have plate operations, a carousel, a sealer, peeler, lid hotel, centrifuge, all the things I've talked about before. And they could be considered base core functionality. But then you have application-specific functionality, plate readers, imagers, flow cytometers, and thermocyclers. Maybe these are only considered and needed on a case-by-case basis, but you might want to bring into the base unit as and when required. So if we could build and deploy these base units across the building, we could essentially simplify the development across the company, simplify training because we've got the same software and the same hardware, but also maintenance and deploying systems across the globe will be massively simplified. So that's why we came up with the flexi-base concept. Each base unit has the core functionality with the cart set that can wheel up on it for each specific use case. We can distribute them across the globe and have multiple systems in the same site. So if we think about platform development not around an application, but on a system that has core functionality that can design all applications, in the same way that you can program something for a PC and have it run on everyone's computer. You can design systems with the expectation of the same functionality across the globe, so there's no trade-offs on, oh, I wish I'd put I wish I'd put that on that system or not, because they're all the same, with only the things on the carts that you need on a case-by-case basis. You can develop, support, and deploy and maintain on that expected functionality. And if you have multiple systems in the same building, you can reduce downtime risk by, rapidly using the concept of built-in redundancy, because if one unit needs to be repaired, you can just move all the use case specific instrumentation to another unit. So by bringing together, really good software onto a base unit that has as much functionality as you need, together with the platform innovation team, is how we unlock scale and develop new screening and manufacturing pipelines at Horizon Discovery. So in summary, science is, moving tiny little bits of liquid around. It's a problem that's misunderstood often, but, has been solved. But I think Workcells are often limited by software and functionality trade-offs, which in many cases makes sense. But, my feeling is that software often holds systems back. So I was looking for a tool that would let me do anything. And I wanted to test that out with a proof of concept in our own time, with our own equipment, with no one looking over our shoulder, but with the ability to tap into support. So once we were happy with that, I could take a step back and think about hardware requirements, less about specific applications and more about standard platforms. And thinking about a standard platform, a flexi-based system where we can design all applications on top of. And I think that makes sense for a global organization. We can build and deploy on systems with expected and known functionality. It allows much easier maintenance and support, and with multiple systems on site, we have inbuilt flexibility and redundancy. And by bringing all these things together with our platform innovation team, we've got cross-functional skills from assay development, data to software, that allows us to unlock that R&D potential and develop a new biological screening and manufacturing platforms at Horizon Discovery. Thanks for your time.
Many thanks, Dave. I do have a couple of questions for you. Why do you think flexibility is more important than application-based systems?
I mean, to put it simply, I guess things change. I mean, obviously, if you just want to do thousands and thousands of RNA extractions, then you don't want flexibility. But I find that, particularly in an environment like Horizon, things often change. And, if we build those applications ourselves, we can also take shortcuts, that maybe, other manufacturers can't do, because we can focus on what we're trying to do in the shortcuts we think are valid for our applications. So, because we've built it ourselves and because we've got that flexibility, when the requirements inevitably change, we've got all that built-in knowledge. We're experts on the system, and then we're in a much stronger position to make those tweaks to the new use cases that come up.
Excellent. And how do you ensure that the end users can use the systems efficiently on a day-to-day basis?
Now, I think this is really important, because I think a lot of people sometimes are scared to use systems. There's complex things, to click on. People are worried that things might break. So when we program these systems, we're really keen to develop a graphical user interface that essentially abstracts the whole system away from the scientists. So if the scientists can only see on that user interface exactly what they need to know about what they're doing, put X number of plates here, how many plates do you want to scan? I find that interface, really builds a lot of confidence in the end users working on that system by just taking away all that complexity and having everything they need within that user interface.
Excellent. Thank you, Dave. I do see we've had some questions come in. So some of these are very specific to the product itself. So what I'm going to do, in the interest of time, everybody, is we will get back to each and every one of you with a summary of the questions that have been asked from the audience and with answers from us. Also, there are several of you that we'll be following up with directly. So one final thing to add, as a company that's based in San Diego, we do have an acceleration lab facility, and our acceleration lab showcases all of our software working with other people's hardware, including mobile robotics. Obviously, we're not going to be flying anybody over to San Diego to see this right now, but we do offer virtual tours on a weekly basis. So anyone on this call or colleagues that would be interested in seeing these devices and the software tools running real time, that's an open offer. So thank you, Tim, Rob, Dave. Thanks for your presentations. Thanks everyone very much for attending. Sorry we overran a little bit. We hope you'll join us next year when we'll be rolling out a series of these webinars with internal and external presenters. And my personal hope is that maybe by the autumn of next year, we'll all